Welcome back to the deep dive. This is where we really get into complex topics and try to break them down into something genuinely fascinating just for you. So, in our last deep dive, we actually walked you through creating your very first 3D print. Getting that idea out of your head and into your hands. It was all about the process step by step. But today, we're shifting focus. We're taking, I think, a really vital leap forward to something that often gets, well, kind of overlooked in 3D printing, the material itself. You
Over.
might see these amazing prints online, right? But the real magic, the core of that final object, it lies in what it's actually made of. Okay, let's unpack this. Because choosing the right material, it's just as critical as the printer you're using or even the design file. It directly controls things like the print strength, its flexibility, how it handles heat, even what the surface looks like. It's what makes an idea really work.
And what's truly remarkable here, I think, is just how incredibly diverse the world of 3D printing materials has become. It's really so much more than just, plastic these days. We're talking about a whole universe of options. Each one has its own unique strengths, its own sort of superpowers, and yeah, definitely its own specific weaknesses, its Achilles heel. So our mission today is basically to give you the knowledge you need to navigate this world. We'll cover the common filaments for FDM printers, that's fused deposition modeling, and then we'll dive into the more specialized resins used in SLA and DLP printers, stereolithography, and digital light processing. We'll look at what makes each material tick, what it's best suited for, and importantly, what kind of challenges you might run into when you're actually using it.
Right. So let's kick things off by diving into that FDM filament world. This is probably what most people picture, plastic on a spool. The range of filaments available just for these machines is incredibly diverse. So we're going to focus on the most common, the most versatile ones first. And you'll see pretty quickly, choosing the right one isn't just about color or something. It's like a strategic decision. And we absolutely have to start with PLA. Polylactic acid. I've heard it called the undisputed king of hobby 3D printing. Why is it so forgiving, especially for beginners?
It really is the gateway material, you could say. And its popularity isn't just hype, it's earned. PLA prints incredibly easily. It has a really minimal tendency to warp, which is a huge plus. And you often don't even need a heated print bed. That simplifies things a lot for newcomers.
Sure.
Plus, beyond being user-friendly, it's made from renewable resources, like cornstarch usually. And it's biodegradable, which, is a nice bonus. And the colors, you can find it in a massive range of colors, different finishes. Makes it perfect for things like decorations, visual prototypes, maybe some fun toys.
Okay, this sounds almost too perfect. If it's that easy and, relatively eco-friendly, why doesn't everyone just use PLA for everything? What's the catch? Where's its weakness?
Yeah, you've hit on the crucial point there. While it's fantastic for those visual pieces, PLA definitely has significant limitations. Its main weakness, liquid temperature resistance. It starts getting soft around maybe 60 degrees Celsius. So like if you print something to leave on your car dashboard in the summer, it's going to warp. Guaranteed. It's also pretty brittle. It can snap fairly easily compared to other materials. So the key takeaway with PLA is this. Great starter material, perfect for visual stuff, low-stress prototypes. But if your part needs to hold weight, or if it's going to get warm, or needs to survive being dropped, PLA is probably going to let you down.
Ah, okay. So think decorative truss pieces maybe, but probably not a durable phone mount for my bike.
Exactly. Not for anything that needs real toughness or heat resistance.
That makes total sense. So if we need something a bit tougher, but we still want it to be relatively easy to handle,
Yeah.
what's the next step up? I've heard good things about PTG.
Absolutely. Moving up that ladder, PET, polyethylene terephthalate glycol.
Yeah.
Yeah, it's often called the golden mean for a really good reason. It's just an excellent all-around material. If you compare it directly to PLA, PETG is, well, significantly stronger. It's more flexible too, and it handles higher temperatures, think maybe 75 to 85 degrees Celsius. But here's the really appealing part. It prints considerably easier than something like ADS, which we'll get to in a minute. It's kind of the best of both worlds in some ways.
And it sounds like it has some other useful properties too, beyond just being stronger.
It does, yeah. PETG is pretty versatile. It's got excellent resistance to water and quite a few chemicals, and it's often certified as food safe, which opens up possibilities for things like custom cookie cutters or maybe parts for kitchen gadgets. So this makes it really ideal for functional parts, mechanical bits, holders, strong enclosures, things that need to actually do something. Now, it does have one little printing quirk that annoys some people. It tends to form these thin, kind of hairy wisps between different parts of the print as the nozzle travels. We call it stringing.
Ugh, stringing. Yeah, I've seen pictures of that. Looks messy.
It can be, but don't let it scare you off. You can usually tune your printer settings, especially retraction, to really minimize it. And honestly, PTG's balance of strength, flexibility, temperature resistance, and relative ease of use often makes dealing with a bit of stringing totally worth it. It's a favorite for many intermediate users.
Okay, got it. Manage the stringing, get a great all-rounder. Now, let's talk about a material that probably a lot of you listening interact with every single day without even thinking about it. ABS. That's acrylonitrile butadiene styrene. The big aha moment for this one is always when people realize it's the stuff Lego bricks are made from.
Yeah, exactly. That instantly tells you a lot, doesn't it?
It really does. Super strong, tough, holds up to higher temperatures, like up to maybe 100 degrees Celsius. But I also heard printing with ABS can be a real headache. What are the pitfalls?
You've nailed its strengths, absolutely. Legos are tough. But you're spot on about the printing challenges. This is where things get, well, genuinely demanding. While ABS is fantastic for making really durable parts, it needs much higher temperatures. Both the nozzle and the print bed need to be hotter than for PLA or PETG. And crucially, it absolutely requires an enclosed print chamber, like a box around the printer.
An enclosure, why is that so critical?
Because without that enclosure keeping the ambient temperature stable and warm, you're almost guaranteed to fight warping and cracking. ABS shrinks quite a bit as it cools down. If it cools unevenly, like the bottom layers are warm but the top layers are exposed to cool air, it creates internal stresses, and the print just pulls itself apart or lifts off the bed.
So if you don't have that setup, you're basically fighting physics. Sounds frustrating. And what about the smell I've heard about?
That's another very important point. ABS releases quite characteristic smelling fumes when it's printing. These fumes contain VOCs, volatile organic compounds. So good ventilation isn't just like a nice suggestion. It's really a necessity for your health and just general comfort in the room.
Okay, so definitely not something you want printing in your bedroom without a window open or an air filter.
Definitely not. But despite these hurdles, for serious mechanical parts, tough enclosures, maybe components for cars where you need that strength, temperature resistance, and the ability to glue parts together strongly with solvents, ABS is still a top choice. You just need to be prepared to invest in the right setup and manage the environment.
Okay, so given those challenges with ABS, especially the warping and fumes, is there maybe an alternative if you need that kind of toughness, but maybe for something that's going to live outdoors, something that needs to handle the sun?
Absolutely there is. If you like the mechanical profile of ABS, the toughness, the temperature resistance, but you need something that basically laughs in the face of sunlight and weather, then ASA is your go-to. That's acrylonitrile styrene acrylate. You can pretty much think of it as an improved version of ABS, specifically for outdoor use.
Improved how?
Well, it offers very similar strength and temperature resistance, roughly in that same 90 to 100 degrees Celsius range. But its key superpower is exceptional resistance to UV radiation and general weathering. Much better than ABS.
Ah, so that's the big difference, UV resistant.
Exactly. This makes it the ideal choice for any part that's going to live outside.
So we're talking things like exterior car trim pieces that are constantly baked by the sun, or maybe sturdy garden tools, or housings for outdoor sensors that need to survive rain, wind, UV without getting brittle or faded over time.
Precisely. ASE delivers that long-term durability and stability when it's exposed to the elements, whereas standard ABS would eventually degrade, get brittle, and lose its color. It's a real workhorse when Mother Nature is part of the equation.
Okay, now, for something completely different. Let's shift gears from rigid plastics to something that challenges that idea entirely. TPU and TPE. That's thermoplastic polyurethane and thermoplastic elastomer. The name kind of gives it away. Their main thing is flexibility. These are rubber-like materials.
Yep, bendy stuff.
I'm thinking like custom phone cases, maybe flexible gaskets or seals, perhaps damping pads that need to absorb vibration or impact.
You've nailed the key applications right there. These materials are incredibly useful for anything that needs that elasticity, that give. However, printing with them, that can be quite challenging. As you might imagine, trying to push something soft and floppy through an extruder isn't always straightforward.
Yeah, I can picture that, like pushing cooked spaghetti.
It's a bit like that sometimes. It usually requires very slow print speeds. And you need a really well-calibrated extruder mechanism, ideally a direct drive extruder, to prevent the soft filament from kinking, bunching up, or getting tangled in the gears before it even reaches the hot end.
So patience is key, and probably a specific type of extruder helps a lot.
Patience is definitely a virtue, yes. And the right hardware makes a big difference. But the results you can get are fantastic for parts that need that rubbery feel or function. And interestingly, despite being flexible, Their temperature resistance can actually be quite good, often around 100 up to maybe 140 degrees Celsius, depending on the specific formulation.
Wow, higher than ABS even. That's surprising for something flexible.
It is, yeah. It makes them surprisingly versatile. I remember seeing someone put custom flexible feet for their washing machine out of TPU to stop it vibrating across the floor.
Oh.
Probably voids the warranty, but hey, it worked. Showed off the material's properties perfectly.
That's a brilliant real-world fix. Okay, so if flexibility isn't what you need, but maybe sheer mechanical toughness and durability, let's talk about a real heavyweight, nylon, or polyamide, PA. I hear this stuff isn't just tough, it's a champion against abrasion, wear and tear, chemicals, and even high temperatures. Sounds ideal for things like gears, bearings, parts under constant stress, but is there a catch? There always seems to be a catch.
Oh, there definitely is. And it's a pretty significant one with nylon. This raises a really important point because nylon has one major drawback. It is incredibly hygroscopic.
Hygroscopic, meaning?
Meaning it absolutely loves to absorb moisture straight from the air around it, like a sponge. And if you try to print with nylon filament that's absorbed moisture, even just from sitting out for a day or two, you're going to have a bad time. You'll get all sorts of problems.
Yeah.
Poor layer bonding, visible bubbling or hissing as the water boils in the nozzle, maybe even steam. And ultimately, your prints will be weak, brittle, and just generally awful.
So it completely negates the whole reason you chose nylon in the first place if it gets wet.
Precisely. So it must be actively dried before you print it. And ideally, kept dry during the printing process, too. People often use dedicated filament dryers, which are basically heater boxes, for materials like nylon.
Okay, so it sounds like a material that really rewards careful preparation and handling. You can't just leave it lying around.
Not at all. Yeah. But if you manage that moisture issue properly, you get fantastic performance, great strength, excellent wear resistance, good temperature handling, usually in the 100 to 120 degrees Celsius range, sometimes higher. Perfect for those high wear, high stress applications we mentioned.
A good tip there, maybe don't cheap out on nylon filament either. Get it from a source that packages it really well.
Excellent point. Quality and proper sealing are crucial for hygroscopic materials.
All right, and finally, for just sheer brute strength in the FDM world, really pushing the limits of what desktop printers can handle, we arrive at PC, polycarbonate. I've heard this described as basically one of the toughest, most impact-resistant thermoplastics you can get for a desktop machine. Incredible strength, incredible temperature resistance. But I'm guessing this level of performance comes at a steep price, and not just money.
You are guessing correctly again. You absolutely pay for that extreme performance in terms of printing difficulty. Polycarbonate is notoriously challenging to print. It needs extremely high temperatures, even higher than ABS, for both the nozzle and the bed. And like ABS, a heated print chamber isn't just recommended. It's pretty much essential to prevent warping, cracking, and ensure the layers fuse together properly.
We're talking really high temps then.
Yeah, think operating temperatures around 110 to 125 degrees Celsius, maybe even higher for some blends. This material is definitely not for beginners. It's for advanced users with printers capable of safely reaching those temperatures, usually modified ones, and for very specific, demanding applications.
Like what kind of applications would justify that effort?
Things like protective covers for industrial machinery, super heavy-duty functional parts, maybe lighting fixtures that need to be incredibly robust and handle heat. That's overkill for most things. But when you absolutely need maximum strength and impact resistance from an FDM print, PE is the king. Just be prepared for the challenge.
Wow. Okay, so beyond these, let's call them pure plastics, the FDM world also has this whole other category, composites and special filaments. It's like taking a base plastic and adding stuff to it.
Exactly. It's a really fascinating area where you can tweak the properties. You take a standard plastic like PLA or PETG or even nylon, and you embed other materials into the filament.
What kind of materials are we talking about?
Well, popular options include filaments filled with actual wood fibers. These give the final print an aesthetic, sort of matte wooden appearance. It can even smell a bit like wood when printing or sanding. Great for decorative items. Then you have fillers like carbon fiber, tiny top strands of CF. Adding those makes the plastic significantly stiffer and stronger, often while keeping it lightweight. Very popular for things like drone frames or performance parts.
Carbon fiber. That sounds like it could be abrasive on the printer.
It absolutely can be. That's a key point with composites, especially carbon fiber or glow-in-the-dark filaments. They can wear out standard brass nozzles very quickly. You usually need to upgrade to a hardened steel nozzle to print them reliably.
Good tip. What else can be added?
You can also find filaments filled with metal powder like bronze, copper, stainless steel. These don't make the part solid metal, of course, but they give it significantly more weight, a nice cold feel, and you can often polish or patina the surface to get a really convincing metallic look. Great for props, statues, things where you want that heft.
So looking back at all these FDM options,
Yeah.
what's the big picture for someone trying to choose? It really sounds like a balancing act.
That's exactly it. Choosing an FDM filament is always, always a trade-off. You're constantly balancing how easy it is to print versus the cost, versus the specific physical properties, strength, temperature resistance, flexibility, appearance that you actually need for your final part. There's rarely one perfect filament, just the best one for a particular job.
Okay, so we've really explored the breadth of FDM plastics from the easygoing PLA all the way to challenging high-performance PC and those interesting composites. But what if your priority isn't necessarily strength or ease of printing, but maybe achieving incredibly fine detail? Or perhaps you need materials for really niche, specialized applications where maybe a liquid starting point is better.
Uh-huh, yes. That's where we transition away from those schools of filament and dive into the world of liquid photopolymer resins, used in printers like SLA and DLP. It's a completely different material philosophy.
How so?
Yeah.
Different philosophy.
Well, with FDM, you often pick a general-purpose material like PETG and make it work for many things. With resins, because the technology allows for such precise chemical formulations, manufacturers offer a huge portfolio of highly specialized options. The choice is almost entirely driven by the desired function of the final part, right from the start. You have your standard resins, for example. These are kind of the baseline, versatile, great for printing, super detailed models, visual prototypes where you want that really smooth surface finish right off the printer. Think miniatures, intricate sculptures, things where capturing tiny features is key.
Okay, so standard for visual perfection. But what if you need that detail, but also need the part to, well, actually survive being handled or used?
Right. Then you'd move to what are typically called tough or durable resins. These are specifically engineered, chemically, to simulate the properties of traditional tough plastics, like ABS or maybe polypropylene, PP. This makes them ideal for functional prototypes, things that need to actually work, withstand some mechanical stress, maybe snap-fit enclosures, jigs, and fixtures used in assembly, or components that might need to flex a bit without shattering.
And I assume there are flexible resins too, mimicking the TPU we talked about.
Absolutely. There are flexible or elastic resins. These are designed to mimic rubber or silicone, and they come in various levels of hardness, usually measured on the Shore hardness scale. They're used specifically for printing things that need to be genuinely flexible or compressible, like custom gaskets, soft-touch grips, seals, maybe prototypes of wearables or ergonomic elements where that squishiness is part of the design.
Now here's one I find fascinating, castable wax resins. You mentioned these are special resins for jewelry and dentistry. How do they actually work? It seems like a very specific application.
It is highly specific, and it's a brilliant link between digital technology and traditional craft. So you print a highly detailed model, say a ring design or a dental crown pattern, using this special castable resin. Then that printed model is used directly in the ancient lost wax casting process. The key property of this resin is that when it's heated in a kiln during the casting process, it burns away completely, leaving absolutely no ash or residue behind.
Ah, so it disappears, leaving a perfect cavity.
Exactly. It leaves a perfect, highly detailed mold cavity in the investment material. This mold is then ready to be filled with molten metal, precious metals like gold or silver for jewelry, or specific dental alloys. It's this incredibly precise bridge from a digital file to a perfectly cast metal object. Really clever stuff.
That is genuinely clever. And perhaps the most critical for certain fields are the biocompatible resins. These sound serious, medically certified materials.
Yes, these are a class apart. These resins have undergone rigorous testing and certification to be deemed safe for specific medical applications, sometimes even for contact with the human body. They are absolutely crucial for manufacturing things like highly accurate surgical guides that help surgeons drill or cut in precisely the right place during operations, or detailed dental models used by orthodontists and dentists, even certain types of medical devices or aids designed for direct skin contact, like custom-fit hearing aid shells.
So with resins, it's less about finding one do-it-all material and much more about pinpointing the exact specialized properties needed for a very specific, often high-stakes application.
Precisely. The resin choice is typically driven by very specific functional requirements, certifications, and the need for extreme detail or unique properties that filament printing might struggle with.
Wow. Okay, we have covered an incredible amount of ground today. From the everyday PLA to super strong PC, Flexible TPU, outdoor ASA, composites, and then this whole other world of specialized resins, it really hammers home that central idea, doesn't it? The right material choice isn't just like a minor detail. It is absolutely key to whether your 3D printing project succeeds or fails. And hopefully now, you listening have a much better framework for thinking about your own needs. What are you actually trying to make? Is it just decorative? Does it need to be strong, heat resistant, flexible? Will it live outdoors? Does it need to be medically safe?
Yeah, what stands out to you from all this information when you think about your next project? It's really essential to consider these factors. Strength, does it need to resist impacts? Flexibility, bendy or rigid? Temperature resistance, how hot will it get? Environment, indoors or outdoors under the sun? And ultimately, what is its specific job? Its function. Understanding these properties, knowing the trade-offs, it really empowers you to make much better, more informed decisions. You can move beyond just guessing or using whatever filament came with the printer and start truly engineering your prints, creating with real intent.
We've definitely explored an amazing diversity today, from that simple, easy-to-use PLA that's great for beginners making decorations, all the way up to incredibly tough nylon for gears and bearings, and those highly specialized resins capable of producing perfect, intricate details for demanding fields like medicine or jewelry. It's a vast and honestly pretty exciting material world out there.
But here's a thought to chew on. What good are all these amazing materials and all this knowledge about choosing the right one if we don't actually have a reliable printer to use them in? Or if we can't consistently get high-quality filament or resin from a source we trust? How much does the hardware and the supplier quality matter in bringing these material possibilities to life?
Ooh, that is a provocative thought to leave everyone with. Something definitely worth considering. Think about all the potential these materials unlock, but also how crucial it is to match that potential with the right tools and critically reliable supplies. We really hope this deep dive has sparked your curiosity and given you a solid foundation for choosing materials for your next 3D printing adventure. Thanks for joining us, and we'll catch you on the next one.